And welcome everybody. I'm Pradeep Khosla. I'm the Dean of the College of Engineering, and welcome to the CIT Leadership Speaker Series. Today is the inaugural speaker series for the whole series. This is the first time we are ever doing it, and I'm really happy and excited and proud to welcome one of our very own, a Pittsburgher, a Carnegie Mellon alum, Dr. Aris Candris. But before I give the stage to him, let me say a few more words about the speaker series. The whole idea of the speaker series is to serve as a catalyst for bringing together internationally renowned thought leaders and Carnegie Mellon faculty, students, and alumni. And clearly, I can see that that is happening. I see in this audience a lot of faculty. I see a lot of some alumni, and I see some students too. The second goal of this is to discuss critical topics that are of contemporary interest, not only to Carnegie Mellon, but to the world at large, and in which Carnegie Mellon has an important role to play or has something to say. And you can very well imagine that the topic of today's talk or conversation is something that Carnegie Mellon excels in and has excelled in for a very long time. We built what I think of as a spectacular program in energy. And unfortunately, it's not nuclear energy. It used to be nuclear energy, and as soon as I introduce Aris a little bit more, you will see that we had a program in that area, but we don't. But we do have everything else except nuclear energy, and we do have a lot of enablers for nuclear energy, like material science, like embedded systems, and a whole lot of other things, except the core nuclear energy program itself. Our energy strategy has been around for about, I would say, more than 25 years. Ed Rubin, who's in the audience, who will be on the panel very soon, was one of the leaders and creators of our strategy a long time ago. But most recently, in the last 5 years or so, we have focused more heavily on our energy strategy, and we have built what I think of as a leading relationship and a spectacular relationship with NETL, which is the National Energy Technology Laboratory right here in South Park. And that strategy has been led by Andy Gellman, who's also on the panel. And that strategy is beginning to pay off dividends, where we have now a 5-university consortium: Carnegie Mellon, West Virginia University, University of Pittsburgh, Penn State, and Virginia Tech, working with NETL on about a $20 million a year program to build all sorts of energy technologies and to position ourselves, not just our universities, but the country, for the future. Let me say a little bit about Dr. Aris Candris. Aris Candris is the CEO of Westinghouse Electric Company, and Westinghouse Electric Company has been a leader in providing nuclear solutions both in the US and abroad, and I think when we hear Aris talk, we will know how much business they're doing abroad. In 1957, when the company developed its first commercial nuclear reactor, Westinghouse is focused on creating sustainable energy, a goal that is shared by Carnegie Mellon and, I assume, the rest of the world. As president and CEO of Westinghouse and as an alumnus of CIT in 74 and 78, Dr. Aris Candris is very passionate about the role of nuclear power, and his master's and PhD are both in the area of nuclear engineering, which used to be as a part of mechanical engineering at Carnegie Mellon. Aris began his career at Westinghouse in 1975 as a senior engineer in the Advanced Reactor Division. And over the years, he's worked himself up the ladder, and on July 1st, 2008, he was appointed the CEO. I think it's reasonable to say he's one of the few people I know who's had a spectacular career in one company for the last 35 years. In this day and age, you don't find that many people of that ilk. Aris has a BA in physics, math, and engineering from Pennsylvania University and a master's and PhD from Carnegie Mellon. He's a member, recently appointed, to the Carnegie Mellon Board of Trustees, but his more important appointment is to the CIT Dean's Council that he attends more often. So, having said that, Dr. Aris Candris.
Thank you, Pradeep. It's always a pleasure to come back to familiar surroundings here at CMU, and this is clearly an honor for me, just to make sure that this paperwork is out of the way. what I want to do here is pretty much set the stage for the discussion that I'm hoping is going to take place when the rest of us take our seats around the table, and make sure that this gets a little bit more interactive. So pardon me if I rush through an awful lot of data and information, but my purpose here is primarily to share some information with the rest of the group so we're all on the same page. First of all, energy demand is growing. Going through in the developed world a lot of efforts to conserve, and those efforts need to continue, but we need to maintain a lot of awareness that the rest of the world is not at the same level as the US and Western Europe in particular, and those countries have a need, a desire, and they're moving along the lines of emulating what we've set up in the last 100 years or so. So the demand is going to continue being there. And you see some of the numbers there, 100 million vehicles that are going to be coming online by 2020 in China alone. And all those will contribute to an overall growth in energy consumption by 2030 that's somewhere around 50% higher than what it is today. So that, by the way, takes a significant amount of conservation in the developed world into account. So that, coupled with the needs that we have in order to make sure that to preserve and even improve the environment, the much more recent pressures on constraining CO2 emissions in particular, kind of limit our options in terms of what we can do. As I said before, conservation clearly needs to be part of the solution, but it cannot be the solution going forward. We do need a lot more balance in how we generate power around the world. China, for example, generates the vast majority of its power right now from coal. We're not all that far behind. About 50% of our power still comes from coal in this country. Then you have on the other end of the spectrum countries like France, where they're 85% in nuclear generation. So the balance needs to change significantly if we're going to have the growth that we need to have and still keep an eye towards the environment. And then start shifting the uses of some of our traditional fuels, especially fossil fuels and petroleum more particularly, but with the use of electric vehicles in the future. And I think that trend is going forward. Let me give you some statistics on the current available sources and the environment. A lot of people, for example, don't know that right now, 3/4 of all the CO2-free power that was generated in the US comes from nuclear power. The other quarter or so comes from hydro. Contributions from solar and wind, at least so far, as you can see, they are fairly small. Similarly, sometimes when we debate these sources, we lose track of what we mean by pollution contribution. You see some relatively unfamiliar statistics up on the board here. The expectation and the impression among the general public, generally speaking, is that solar and wind don't have much of a contribution. Well, when you consider construction-related pollution and manufacturing-related pollution in the equation, you see, for example, that natural gas can be better than some ways of solar photovoltaic and so on down the line. Clearly, hydro continues to be a very good source, but it's very limited in terms of availability going forward. Same thing on costs, and these statistics always have to be careful when you quote statistics, and especially from your end, a lot more careful when you read them, because they're, as Disraeli used to say, the lies, damn lies, and statistics. So in this particular case, these are statistics from installed capacity. So when you look at installed solar, installed wind, and so on down the line, there is significant difference in generating costs. Nuclear, by the way, for installed generation has been for the last 10 years or so the cheapest way across the board in the US and most other places as well. Part of the reason for that, again, in order to make sure we're all operating the same data, is that capacity factors of nuclear are very high. They didn't used to be. It took us a while to get to where we are right now. Back in the 80s and even early 90s, we're still struggling in the 60 to 70% capacity factors. We're now consistently over 90% and have been for the past 10 years. As a result of that, The costs are going down and the reliance is going up. But you see the rest of the statistics there. Another piece of information that needs to be communicated is in the case of nuclear, in the case of hydro, in the case of wind, in the case of solar, capacity factor and availability is about the same. That does not hold true for gas especially, but also for coal and oil. We don't run those units whenever they're available for obvious reasons because of cost and pollution. So the bottom line, if there's one message I want to leave with this group is I'm not up here to advocate that we should shut everything down and build nuclear power plants. But the need for a lot more balance in our mix going forward. And having said that, let me now go to an area that I know a little bit more about than the other, and that's nuclear, and kind of run you through what I call a nuclear primer here in terms of some of the things that have changed in the last few years. Back in the 70s, okay, which is basically some of the bullets that you see up here, we're making it up as we're going along, both in design as well as regulation of the industry. A lot of changes. As a matter of fact, 104 nuclear power plants that we have in the US right now, none of them has identical design with any other of the plants. Even on the same site, you walk to one of the units and you go to the unit next door, differences in design. The reason is that we were basically completing the designs, improving the designs, expanding the designs, and the output of these units as the units were being built. It didn't help with regulation. It certainly didn't help with construction costs and construction schedules. Regulation was also something that was fairly new, and we're making it up as we went along. In the midst of that, 3 Mile Island happened, which escalated quite a bit the amount of regulation in the industry. We learned quite a bit from that. Actually, at the time that it happened, it was totally catastrophic. It stopped basically dead in its tracks, nuclear expansion in the late 70s, early 80s. But in retrospect, it's probably the best thing that happened for the industry. We learned quite a bit from, not only from the accident, but also in terms of operations. As you see in the bullet there, a lot of the operators that bought those units in the late 60s and early 70s bought it as another way of boiling water for the turbine, okay, and generating steam. Obviously, it is a little bit more complicated than a gas turbine plant or a fossil unit of any kind that they had before, or even more so, a hydro unit. And it's taken a while for the industry, or it took a while for the industry to catch up with that. And I was absolutely delighted that when we had the problems in the Gulf and we looked at what was missing in terms of regulation of that industry, just about everybody who's knowledgeable about how different industries are regulated in the US turned and said, you need to take the example of how nuclear industry regulated itself after 3 Mile Island. So a lot of lessons learned is the bottom line, and the most important one is in the area of construction. I'll give you some examples of that in a couple of slides. Obviously, we've made a lot of strides since then. Today, nuclear power in the US is about 20%. It's a little less than that worldwide. It's about 16, 17%. But that percentage is going up because a lot of the developing world is building a lot of nuclear units right now. There are about 59 units under construction as we speak. China alone is going to be putting another probably 80 units between now and 2020 under construction. So we're going to get to a stage where China is basically putting almost a unit a month online of nuclear units. But back to this slide here. At the same time, the regulatory process, we took time in the hiatus that we had available to us in the 80s and 90s to work with the regulator and develop a much more streamlined process for these plants. So right now, if you have a pre-licensed design in a pre-licensed site, and you put those two together, the opportunity for intervention and the uncertainty associated with that is very limited. So the utilities can get to a stage where they basically start building the plant, and they almost have 100% assurances that that plant is not going to have any additional regulatory hiccups down the road. The designs have improved a lot. I'll show you again in a minute some examples of the type of simplifications, for example, we put in our design as a result of the development that took place in the 60s and 70s and then 3 Mile Island. We put an awful lot of regulatory mandated Band-Aids on the original design. We took a look at that and basically changed it drastically. We also have a track record we didn't have before. We now have several thousand planned years of safe operation of nuclear power in the Western world. And then advances in modular construction and other construction techniques have significantly improved our chances of delivering these units on time and on budget. Let me get a little more technical on you. I promise I won't go too far into the details, but what you see on the left is what we're left with after 3 Mile Island, and a number of other changes have taken place before that. In the center is what basically generates the steam that goes out to the turbine generator in that gray box. All the rest that you see around it is pumps, valves, piping, diesel generators that was added on in order, in case of an accident, to maintain a coolable geometry in the reactor. In other words, keep the plant cooled and safe for the rest of the time. What you have on the right is what the same plant basically looks like now. That's the Westinghouse design, by the way, so it's a little different than the rest, even more simplified than the rest. We basically have done away with all the active systems for safety and rely on two things, gravity and convection. And it still took us about $100 million to prove to the regulator that water does still flow downhill still. But it was money well spent. The design is a lot simpler, as you can tell, than before. And again, the fact that it is simpler contributes to shorter construction times, as well as cheaper operations and more streamlined operations going forward, and shorter schedules of construction. What you see here is basically some of the other things that we decided to upgrade during that hiatus period between 3 Mile Island, roughly, and a few years ago when the nuclear resurgence came back. I talked about the licensing upgrades. We also found out when we're building the first generation of plants that an awful lot of the schedule issues and cost overruns were associated with the construction itself. In other words, the fact that you're building such a complex plant out in the open, in the elements, and you have to spend several years there with usually transient labor, does not help. So what we try to do is minimize that. So now we build most of the plant in a factory environment. We build it in modules, and those modules are transported to the site, and that simplifies construction, improves the quality control, obviously, because you're doing it in a factory environment, and reduces uncertainty overall. One example of that, and one example of the simplifications I was talking about earlier in terms of going to passive systems, is the overall reductions in the hardware. And it can be as drastic as piping. We have 80% less piping in this plant than a standard old plant or a competitive plant right now, and 85% less cabling. Obviously, a lot of it has to do with going to INC from analog systems, just to be absolutely transparent. But again, a lot less concrete, a lot less pumps and valves, which again reduces cost, reduces construction schedule and uncertainty. The first of these 4 units are under construction right now in China. They're scheduled for completion in 2013. And you see some of the pictures here are obviously construction progress pictures, but in the one in the lower center, as well as here, you basically see one of these modules being put into the inside what's called the containment building. And just to give you an idea of scale, because it's very hard to lose sight of that, that's about 6-story building equivalent. That's the white portion that's being lowered in there. Okay, so a lot of large modules that are being constructed now off-site and being brought in, again, improving schedule certainty as well as quality of construction. So not your father's nuclear power plant. Is that, for those of you who remember that ad from Oldsmobile a few years ago. In terms of where we are globally, first in the U.S., 22, about 11, 12 utilities to be precise, have stepped forward and asked the NRC to start the regulatory process. 6 of those have advanced enough to have engineering, procurement, and construction contracts completed already. All 6 of them, by the way, are for AP1000s, the Westinghouse design. So very happy. They're the ones that you see with an asterisk there. 4 of those are under construction right now. The non-nuclear portion of the construction is already started. The nuclear construction is going to start about this time next year. The rest of the world is really where the majority of the story is right now. We have been contacted by no less than about 50 different countries who want to start a nuclear program over there. And clearly we're not chasing all 50 of them, but there are some that have established or in the process of establishing very robust programs in place, both the manufacturing as well as the regulatory component of that, and you see some of them over here. Let me give you an idea of what I'm talking about so you get a pretty balanced view of what the nuclear world is going to look like, and that's going to a preamble to the discussion we're going to have as a group later on. This is where the concentration of nuclear plants is right now. As I said, you have about 104 units in the U.S., exactly 104 units, as a matter of fact, not about, that are generating about 20% of the electricity. You have countries like France with about 85% of the electricity being nuclear, and you see a lot of concentration in France. Western Europe in general, Sweden, Germany, Spain, Belgium, UK, large percentages in the 30s or so of the generation is nuclear. And then you go in the Far East, Korea, Japan, Taiwan, again in the 30s in terms of nuclear generation. That's the current picture. Then you fast forward to 2030, when you're going to basically add another 50% to the current generation. And you see a slight shift, a lot more in Asia and than before, but clearly not enough by comparison to what are the plans for 2050, where you see a total shift in the balance of nuclear generation. A lot more in Western Europe, but then Western Europe is very densely populated. The same thing holds true for Japan and Korea and Taiwan. But the big story is India and China, where they have made already commitments for significant increase of installed capacity. As I mentioned earlier, the Chinese in particular have a very specific program of nuclear construction, and they're going to stick to it. And of course you see places that we haven't been before, Africa, for example, and Southeast Asia and so on. So at some point, based on current plans, part of what we need as a country to look at is whether we're going to stay relevant in this debate. If the nuclear power plants in the U.S. represent 2% of the population of nuclear units around the world, we're not going to be particularly relevant in the debate and won't have as big a vote as we have right now. So in summary, clearly we need to have means of meeting our energy needs that are safe and environmentally agreeable. We do need to continue advancing renewable sources, but we also need to stay balanced in terms of on making sure that we also have the bedrock of our current generation capability, which is the base load plants, and continue to make a shift to more environmentally friendly base load in order to be able to meet some of the rather lofty, I think, especially in the Western world, goals that we've put in place for reduced CO2 generation going forward. Thank you very much, and when we sit down as a panel, we'll have an opportunity to answer a lot of questions, I'm sure, from all of you. Thank you.
So what we're going to do is, I'm going to introduce the panelists real briefly, and as I say your name, please come and take your seat, I guess, even before that. Please. And I'm going to start with a couple of questions that I have, and then open it up to the audience, and if you don't have enough questions, I'll fill the hole. So first, let me introduce Dr. Andy Gellman, who's the department head of chemical engineering. He's also the founding director of the Institute for Advanced Energy Solutions, which is the name of our partnership with NETL that I was mentioning earlier. Next is Dr. Ed Rubin, who's the Alumni Professor of Engineering and Public Policy and Mechanical Engineering. He serves on the NRC committee studying climate change, mitigation policies, and energy R&D planning and alternative transportation technologies. And he was the member of the IPCC that wrote the report for which Al Gore and the IPCC got the Nobel Prize. Dr. Jay Whitacre, next to him, is an assistant professor of material science and EPP, and his current research focuses on synthesizing and implementing promising materials and device architectures for energy storage. He's on leave this year doing a startup to look at a new class of batteries that are going to be really cheap and free for everybody, and we can store the energy. With that in mind, let me start with Aris. That was a very interesting and an illuminating talk where I didn't quite appreciate how many nuclear power plants are being built across the world. And I was always under the impression that there is a big pushback by society in general against nuclear power plants. So given that impression, especially in the US, and given what you're predicting out here, what is it that needs to be done to educate or inform or make people more aware of the positive attributes of nuclear power? What is Westinghouse doing? And in that context, how can Carnegie Mellon be of any help or use to Westinghouse, both in generation of technology and?
Thank you. Yes. First of all, we start with the last part, which is the easy one. I mean, forums like this are important to get the word out, and so appreciate what you guys are already doing in helping to get the word out. Is this on? Yes, it is. Okay. But because going back to the beginning of your question, one of the biggest problems that we've had in this industry, and it's a problem that we created, quite frankly, is we do not communicate enough with the general public. Early on in the 60s and 70s, there were folks in white lab coats that were working on nuclear power, and they figured this is too complicated to try and get out there and explain to mom and pop and a bunch of housewives. Absolutely wrong tack. And we still are doing ourselves a disservice by not going out and being a lot more aggressive in communication. Now, having said that, the statistics, especially in the U.S., are a lot more encouraging than you think. In spite of a poor job we've done, most of the American public has gotten the word, and the general acceptance of nuclear is an all-time high right now. A lot of it has to do with the fact that finally the word got out that we do not generate any CO2 gases or any other pollution of any kind. But even before that, there was a slow recognition, especially with years of experience and operating record behind us, that these plants are indeed safe, good neighbors, and can be run at very profitable levels. So right now, the general acceptance of nuclear in the U.S. is somewhere in the 70% range, which is significantly higher than what it used to be a few years ago. What's even more telling is if you go to the areas where the nuclear plants are, the acceptance rate is well over 80%, and that does not include the folks that are working in the plants that are associated with the utilities. So those folks have been working and living, and experiencing close up the plant as a neighbor, and they feel pretty good about it. Long-winded answer, but I think that covers it.
No, that's actually very useful. I didn't realize the acceptance rates were that high. Andy, let me ask you a question. I know you're leading this effort with NETL. So we heard Aris talk about an energy future that seemed to me was going to be like a portfolio of energy technologies, and not just A or B or C. And I know you've had visions about that in terms of what you're doing with NETL. Can you tell us a little bit about what would that portfolio look like? How long would it take to get there?
So, yeah, I think the reality is the portfolio terminology is the right one, and the fact is it's going to take probably hundreds of years to get to a point where we're in some sort of steady state. So my view of the energy world is that we are where we are today, which is largely 70-80% fossil-based energy and 20, maybe 30% other sources. There has to be a transition over the course of time because fossil resources are limited, although truthfully they could last for hundreds of years. And given the wrong economic pressures, they will last for hundreds of years. So over the course of a few hundred years, you have to have a transition from fossil-based to something else. And something else has to be either renewable or at least something that would be an energy source that exists for as long as civilization wants to exist. So, and I personally suspect that the real time frame for getting to a point of sustainability, if you like, is of order 200 or 300 years.
So that's very interesting, and I think that kind of relates to, so let me read a statistic for you. And this is from the U.S. Energy Information Administration report. In 1980, fossil fuels were 90% of the total power generation. In 2006, 26 years later, they were 86.2%. So there was hardly any movement of the needle, as one would say, right? And nuclear power in 80 was 2.6%, and nuclear power in 2006 is 5.9%. This is across the whole world, right? So it's interesting that you say it would take a couple of hundred years. I can very well imagine at this rate, it is going to take a couple of hundred years. Ed, let me ask you the following. So if we then think about a couple of hundred years, and if we think about keeping on emitting CO2 in the meantime, because fossil fuel is the dominant fuel, our president and the senior leadership have laid down this vision of reducing CO2 emissions by 80%. How are we going to do it, and how fast can we do it?
Pradeep warned me not to give a long lecture on this, but this topic cries out for a little bit of background. Most of you are familiar with the climate issue, but the 80% number needs to be put in context. That number didn't come from the administration. It came from the IPCC, the group of scientists who've been studying climate change. And what they're suggesting is that the world, on average, needs to reduce its emissions of greenhouse gases by about 80%. Here's the clincher, not in 200 years, but in the next 40 years, by mid-century, 2050. Why? To avoid what appear to be serious consequences of climate warming if we don't. The administration has adopted that as a policy. They didn't succeed this year in getting it. The state of California did. The state of California, in fact, has a policy that would reduce its greenhouse gas emissions by 80% by 2050, very ambitious. That driver is probably one of the strongest reasons for the renaissance of nuclear power, because it is one of the few, as I already pointed out, near zero emitters of CO2. But I also want to make sure that we don't leave the room. When we talk about energy, we tend to focus on energy supplies. When I think about energy, I start with energy demand. If you think about how to reduce CO2 emissions significantly, the only truly clean energy I know of is energy that we don't use. Everything else has some baggage. And so the first place to start for reducing emissions is in reducing demand for not just electricity, but energy across the board. And the U.S. is the obvious place to start. We're less than 5% of the world's population. We produce something like 15% of the world's energy, and we consume over 20% of the world's energy. We can do better than that. We know how to do it. We've lacked the political will. So energy efficiency and energy conservation is the place to start. Switching from high carbon to low carbon fuels, from coal to natural gas, can bring us halfway. Nuclear, along with renewables, have a very strong potential role. But again, all of these other things have other kinds of impacts. And the fourth option that's getting a lot of play now is a technology called carbon sequestration, capturing and putting carbon dioxide deep underground as a strategy for at least several decades that can deal with a large amount of coal that's going to be used. So it's all going to depend, I think, a lot on policy. It's not going to be easy to do. It may not even be possible if we don't start soon, but there's a major challenge out there.
So thanks, Ed, but I want to come back to this in a second because I still am confused. One of you says it's going to take 200 years for a transition, and you are going to reduce CO2 by 80% in 20 years. It seems to me that the transition shouldn't take that long, but I'll come back to that. But think about it, but I want to get to Jay Whitacre in the meantime. So if I were to believe this portfolio of energy strategy, as in multiple sources of energy, clearly smart grid is going to play an important role. And clearly, as I look at the pictures that Aris was showing, intermittent energy sources would have to have storage capability. So can you say something about what are we doing in terms of new materials, new batteries? How cheap are they going to be? How affordable are they going to be in terms of large-scale storage? Are we going to get there or are we not?
Of course we're going to get there.
Yeah.
In a couple hundred years.
That's too long.
No, so yes, your question is appropriate, obviously, for what I'm working on. And the answer is there are many there's a whole portfolio of different approaches, as there are in many emerging energy technologies right now. There's a whole portfolio of possible solutions sort of battling it out right now for dominance. Many of them are based on what I consider to be technically superior solutions that are also economically severely disadvantaged. And the people who are going to win at the end of the day are those who bookkeep the performance of storage on a dollars per kilowatt hours delivered over the lifetime of the device. And if you cannot compete with pumped hydro, which is at about 2 cents or 3 cents a kilowatt hour, you probably you might have a shot because the only competition there are giant lakes, essentially. But the real competitor right now are stationary, put up to be run once in a while, what are called peaker plants. These are large gas turbines that cost in the order of $700 to $1,000 per kilowatt hour installed, and they run on natural gas. These are what we really have for energy storage right now. If a large wind farm goes down quickly, loses its ability to produce power because the wind is curtailed, they spin up these turbines to buffer out and to level out the demand. And if you can instead make an energy storage device that will deliver energy over a 3 to 6 hour time frame, you might be able to offset some of this. And so the price point has to be from some kind of battery level, something that's under $300 a kilowatt hour. To put that in perspective, and it has to last at 10 to 15 years, and it has to be able to have very good round-trip energy efficiency. Right? These are very tall demands that are placed on these materials and this innovation. So it's not, is anyone there yet? No, no one is right now. Lead-acid batteries are cheap enough, but they don't last long enough. Lithium-ion batteries have a good performance, but they're 2 or 3 times that expensive, and they also have difficult thermal ranging problems. They can't get that hot or too cold, and they are inconsistent if they are run sort of at deviant temperatures. So, but there's 4 or 5 emerging solutions that are going to be able to compete and maybe make a difference. We'll see what happens, but everyone is sort of edging closer and closer to this cost point. It starts with, do your material systems that you're working with at a raw materials level, can you scale them to the right cost point? Can you insert them in a system where the balance of system is also not that expensive? And then can you stack up against a competing technology like a natural gas-fired turbine? If you can't do those things, you're not going to win. So it's going to be a long time, I think, but we're out there trying to make this work.
Thanks, Jay. I'm going to open this up to the audience. I'll pose one more question, but go ahead. If you're ready, go for it. Actually, there are microphones in the... So there's one to my left near that window, and there's one to my right out here near the window. So while you're walking up there, let me pose a question to the whole panel out here. So if I look at the strengths of Pittsburgh, clearly Westinghouse right in our backyard is a great strength. NETL on the other side, our other backyard, is a spectacular strength. Carnegie Mellon, University of Pittsburgh, Penn State in the 2-hour vicinity, WVU are other great strengths. So I'd like you to tell us a little bit about what do you see as an economic development opportunity that we could be exploiting? What role can Pittsburgh have in the energy future of the world?
I would even go further than that. If you look at Marcellus Shale under our feet here, EQT and other companies, Consol is also in both the coal now and the gas business. So part of what we're trying to do is basically get us all together, since we're all trying to advocate for improvements in this area. We're also trying to advocate for this area to be regarded as the Houston, the new Houston of the U.S., and we're starting to get some traction. We do have a group of companies that comprises all these areas that get together periodically and try to plan and along these lines and try to project Pittsburgh in this light, and includes not only the traditional sources, but wind and solar and smart grid and some of the other more innovative and newer technologies are starting to spring up, some of them as a result of CMU and Pitt being in the area and people wanting to stick around. So we are in the process of doing that. I even see some people back there that have some affiliation with that group, so we'll keep trying.
What about startups? Jay, I know you're involved in one.
Yeah, so my addition to that is that we need to do whatever we can to lure. There's a lot of money out in Silicon Valley, mainly right now, these new venture funds. The venture funds are starting new funds explicitly for developing new clean energy technologies, and there's a lot of money out there. They're multi-billion-dollar funds, and they are looking actively for people and ideas and concepts, both for growth investment as well as incubation investment. And we need to continue to court this kind of thing because the more we establish in the region, I think the better off we'll be. And we have to make sure that these companies keep their roots here as well, because that's another huge deal.
And what are we doing about any policy that we could give some advice to Dan Honorado and company? Anybody from his office here? I hope so.
If there aren't, we can ask them why they're pushing aggressive, expensive solar technology over some other things that might have. But we won't have that discussion here. I think that's another strength certainly of Carnegie Mellon. We've both, especially in the engineering and public policy department, we have I think a very long and well-established history of trying to look sensibly across the spectrum of policy options and offering up good advice.
Andy, does NETL have it in its plan to seed some companies, do transition? Any comments?
NETL would certainly be more than happy to take any technologies developed around here. And I think one of the potential real values of having 5 universities is that you have 5 universities, each of which has its own independent intellectual property portfolio, along with NETL. And if we were able to organize things well enough to say, well, we can take a piece from here, a piece from here, a piece from here, and suddenly put together a new technology, that would be awfully useful. In fact, among any grouping of universities, that would be an incredibly valuable exercise.
Thanks, Andy. I see lines forming on both sides, so just one piece of advice, make it a real question, very crisp, because I would like to get to all of you and maybe more people. Just your name and the question, please. Sir?
Okay. I'm Don Firesmith. I work at the Software Engineering Institute. The question's for Dr. Candris. What is the nuclear industry doing in general, and Westinghouse in particular, with regard to securing the nuclear plants from cyber terrorism and cyber warfare? I mean, we've already seen that we can destroy turbines from the outside and that you can't build them very fast.
For the current generation of plants, even though there are things that we're doing, we can't really talk about them, but I can tell you at a 50,000 foot level, they're a lot more immune than all of other parts of infrastructure because, unfortunately, they're using 60s technology for INC, which is not as susceptible to intrusion from the network in terms of control. So there's something going for it for not having renewed our infrastructure in the last 30 years or so. Going forward, clearly it's a design criterion. It's something that we're looking at, that we've looked at even before it became fashionable. And as a matter of fact, we are working with CMU, among others, in order to make sure that we put robust features in place. Interestingly enough, by the way, when it comes to security in general, right after 9/11, there was a big flurry of activities by the federal government to look at our infrastructure as a whole. And they even devised some sort of a scale, A, B, C, D, in terms of grades that you got. Nuclear power plants was the safest part of our infrastructure, bar none.
Thanks, Aris. It seems to me that between SEI and Scilab, you have all the solutions at home. Go no further.
Psychology. I was just wondering, why isn't the price of the uranium metal rising along with other commodities? I understand the decommissioning of weapons is part of that. My second question is, what's the plan B for the waste after the feds declined Yucca Mountain?
Good question.
I guess they're both for me, so. The price of the uranium is partly for the reason that you mentioned. The federal government is taking both U.S. and non-U.S. weapons grade uranium, and we're down blending it. Matter of fact, Westinghouse is doing most of that, and using it in commercial plants. And that obviously keeps the price overall down. But in general, uranium is not a scarce resource. There's a lot of misconception about that probably stems from some of the cartoons back in the 50s. So it is not all that susceptible. Even if it were, let me just go a step further, there was a time when there was a spike in the price. It went from about $10 to $140 about 3 years ago or so, and stayed there for a few months and came back down and crashed. But even during that period of time, it didn't affect the cost of electricity generated from nuclear, because the cost of fuel is a very small component of these plants. And again, one of the reasons that utilities like these units is they're not susceptible to these types of price fluctuations that we have with gas prices and the like. Let me go to the second part, which is probably more interesting. I keep correcting people, and I apologize for doing that to you, but it's not nuclear waste, it's actually spent fuel that we're dealing with. And a very big distinction. What comes out of these plants still has about 85% of its energy content in there. So a once-through system, the one that's been adopted in the past in the U.S. and it's being revisited right now, is almost a crime. That you put that much usable energy and bury it away. For political reasons, to make a long story short, Yucca Mountain, at least for now, appears to be sidelined. And I'm a lot more optimistic in my comment than I think what you get in the newspapers, because I think that's going to come back and be an available part of this, or part of the available solution. But in general, I think we need to be going back and looking at how we close the most effective way the fuel cycle. France is doing it with Westinghouse and U.S. technology, and have been doing it for a number of years, and we need to go down a similar path. I'm not advocating use the same technology. We've come a long way since then. This is technology that was developed in the 60s, but we're now looking in the U.S. There is a Blue Ribbon Commission that's been established as a result of the political decision on Yucca Mountain, and part of the recommendation is, how do you burn this fuel differently? How do you reduce the actinides in the fuel, which is the bad actors in the fuel? You can do that with technology now. And how do you develop new technology to reprocess and recycle that fuel? Okay. Eventually, you will have some waste. It's a very small portion of it. By the way, there's a lot of misconception about waste in general. I was telling somebody earlier that one of the reasons that when I was a long-haired hippie here on this campus back in the early 70s, that I went to nuclear engineering is because when you look at it, it's the only source of power available to us, large scale, that can truly deal with its waste. The sum total of the waste from the 104 plants that we have now after 40 years of operation is about a football field, 20 feet high. It's less than 1 year's coal ash from a large fossil plant. And people sometimes lose sight of these numbers. We have the luxury of waiting and finding a much more elegant solution. 100 years ago, we couldn't even spell nuclear. 100 years from now, God only knows what's going to be available in terms of technology. Going and burying once through this spent fuel in the ground, as I said before, is not the right solution.
Yes, sir.
I'm Christophe Kunwell. This question is more for Dr. Candris. I'm wondering, you mentioned previously shale coal, shale deposits that were available. And I was wondering, do you think that the increased availability of fossil fuels and non-sustainable resources will impede the development of nuclear technology and nuclear energy?
I can tell you definitely that the low price of gas in this country has delayed the next construction of nuclear units in the U.S. And in a sense, that's unfortunate, because this is short-term thinking versus long-term solutions, and it kind of advocates for what Andy was talking about. It may take us about 100 years or so in order to get this right. That is not an issue, and it's not a factor outside the U.S. Shale gas is primarily a U.S. gift, and I think by the time we're all said and done, and we truly identify the true cost of extracting shale gas and dealing with some of the pollution issues associated with it, there's no such thing as, a free lunch. So right now we're dealing with almost like the way we dealt with nuclear power back in the 50s, and we said it was too cheap to meter. Okay, so gas is not going to be as big a factor. But right now, yes, the overabundance of gas and the low price is affecting decisions.
Let's see on this side. I'd like to give Aris a rest for one question. Does anybody have a question which is not for Aris so he can recover his voice? I guess not. It's your turn. Go for it.
Yes, my name is Lauren Fleischman. I'm a PhD student in engineering and public policy, and I study public perceptions of low carbon electricity generating technologies. And I just actually wanted to get your reaction to something. I'm really specifically interested in people's gaps and misconceptions about different energy technologies. And I agree with you that nuclear has become more accepted by the general public, though I wouldn't paint as rosy of a picture as you would, because I just did a study with 58 science, 6th through 12th grade science teachers in the area, and I asked them a true or false question. The question was, nuclear power plants release no CO2 into the air. A quarter of the science teachers answered incorrectly, and about 20% said they did not know. And this is the science teachers. So, you know, the message is, you know, is out there, but not at the level I think that you would want. And it's also, it's something that, you know, we have to watch what we think people know. And I wanted to get your reaction to this, if you've heard this before or not, that people actually think that nuclear power plants release CO2.
Well, absolutely, yes. I've heard that. I'm also quite aware that there's a lot of information gap, and that's why I answered the question early on, that I think we need to do a lot better job in communicating, and especially targeting groups like science teachers that ought to know better.
See, I'm Bernard Cohen from University of Pittsburgh. I do writing and speaking on behalf of nuclear power. The pushback I get that I have trouble with is on the cost. You seem to say that the cost has been going down, but several years ago it was $2,000 or $3,000 per kilowatt. Now they're talking $5,000 to $8,000 per $1,000 per kilowatt. What's going on? Why does the cost keep going up that way?
Okay.
Wait, this is the installation cost of building the plant? I just want to make it clear to, right.
And first of all, on the construction cost, the numbers that are out there are not always correct. Okay, the numbers that were quoted early on were a little bit Pollyannish by the industry. There's no question about it. On top of that, we had an across-the-board increase in materials. Concrete has gone up significantly. Steel has gone up across the board. It's affected the construction of all kinds of infrastructure. But obviously, we're the beneficiaries of that as well. Having said that, some of the numbers that are being quoted now, and they're quoted by our customers, so obviously we can't step out there and say these numbers are wrong. It includes a whole bunch of the infrastructure and contingency that they, as prudent project managers, have to put in on their books before they go to the PUC. So the numbers that you quoted includes not only the overnight construction cost of the plant itself, but putting additional lines into the plant, building roads, building to support the plant there, transmission and transformers and so on. So it is significantly higher than the cost. I mean, those costs, those adders would have been there in a non-nuclear facility as well. But it distorts a little bit the picture from the numbers that were originally quoted just as overnight costs for new plants. The overnight costs right now for a plant in most Western countries is somewhere in the neighborhood, for our unit, somewhere in the neighborhood of about $4,000. And we hope to get it back down to $2,500, by the way.
So we're going to finish in about 5 minutes, and then we'll have a reception, so you'll have a chance to meet with Aris on a personal basis. Before I get to you, let me pose for the panel a question on smart grid. That's an issue we have not talked about. If you look at this multi-source enabled future, clearly smart grid technologies have to play a critical role in enabling managing the power all the time. So Aris, let me start with Jay and come to Aris, because I want to know what Westinghouse is doing about it. But before I get there, let's start with actually Ed. He's been quiet for a while. Do you think the smart grid has any reasonable chance of happening in the next 10 years or 20 years? I want to see what your prediction is about the smart grid.
how smart do you want it to be?
So imagine a grid where power is being auctioned in real time and where people are buying and selling power literally from their houses.
My hunch, Pradeep, is that conceptually the notion is good. We know where we ultimately would like to get to. To do this on large scales is going to require time, as it always does for any new innovation. But what we're talking about is technology that can enable all sorts of things we can't do now, anything from moderating appliances that aren't being used in homes and buildings to reduce energy demand, to be able to handle fluctuations in intermittent sources like wind and solar, which actually makes baseload technologies like nuclear and others more efficient and lower cost. But it's going to take time. This is the right, we're probably overdoing getting it started, but we're on a path. Look back 10 or 20 years from now, students in the back of the room, remind yourself to ask the question in 20 years, how smart is the grid now, and how dumb was it when we heard this picture back in Carnegie?
So let me then go to Jay. So Jay, you're working on storage and you think that's one of the key enablers. What capabilities does a smart grid need to have to understand it needs to store energy, it needs to pump energy out, at what price it's storing, at what price is it selling? How does this all work?
I mean, it's difficult. It's one of the questions of the smart grid is not only how smart is it, quote unquote smart is it, but also how distributed is it, right? And the more distributed you become, the more useful smaller storage bits are, and within a given node, are you having a great deal of intercommunication between the nodes, or are you just having one node take care of itself and have a very single link out between them? I mean, there are many architectures, I guess is what I'm trying to say, and it's unclear which one's going to be the dominant one. And so there are many development paths right now. Some are looking on my side at what's called community energy storage, which is 25 kilowatt hours dedicated to several households, sort of at a block level. And these are across the countryside, right? This is what AEP was looking at, for example. And then there are other people like AES who just want to do like 10, 20, 100 megawatt hour things at, near the production point or near like major nodes, right? They're both valid. They both require a different kind of intelligence, and it depends also on how interactive you want the purchasers, the users, the public to be. It might be that we put that at premium and put a battery in our basement instead. It's 5 kilowatt hours, and we can decide to use it for our own good, or we can decide to sell time from that battery back to the grid, right? If that is the answer, then you have to have a great deal of intelligence. If you keep the battery at the node level, it's a much different kind.
So Aris, what about Westinghouse? What are you guys?
Pessimistic as Andy was earlier, I'm not going to go to 100 or 200 years, but I think 20 years probably optimistic for the U.S. One of the disadvantages that we have for being innovators in this country and have one of the oldest grids as a result of that is it will take trillions of dollars, literally, in order to upgrade it to a point where we can do everything we want to do and would like to do with a smart grid. Having said that, as Ed said, nuclear is really a beneficiary of a levelized demand system, and that's exactly what a smart grid is doing. So we're waiting and hoping.
Andy, do you have anything to add?
Yeah, I'll just say I'm too inexpert in that to have anything useful to say.
Oh, okay. So, I see 3 people waiting in line. I'm going to predict they're all for Aris. All the questions are for Aris. Did I get that right? Maybe not. Good, thank you. So let's start with you, and then we'll finish with 2 out here, and we'll be done. So be quick.
My name is Richard A. Flady, and this is for Dr. Aris. For a typical AP100 nuclear steam supply, now that's excluding the electric generation portion of a plant, what portion of the construction costs and the labor costs will be in the U.S. Now, in the U.S., what portion will be sourced inside the U.S. versus offshore?
For the nuclear portion, I would like to say that at some point we'll be able to be at 100%. Right now, because we've let the infrastructure, not only nuclear, but across the board, all the supporting infrastructure, foundries and the like, go by the wayside in the last 20 years, we can't do that. So for example, for the large components that we need one-piece forgings, we have to go outside. We go to Japan, we go to Korea. Down the road, even India, the UK and other countries are developing that capability. We're still lagging behind. So right now, probably about 70% of the content is US based. The rest of it will have to go outside.
My name is Adam Colt. I'm a graduate student in civil environmental engineering. My question's for anyone in the panel who can answer this and wants to. What is the future of nuclear breeder reactors? Dr. Candris was talking about earlier, not doing just the once through. What is the future of that, and how close are we to it?
Well, since I started my career designing those suckers back 35 years ago, I can tell you that we've gone through the first phase of development and actual operation, both in the U.S. and especially overseas. We have a lot of data from successful operation, but in terms of commercial operation of these units, I don't think anytime, at least in the foreseeable future, we're going to see breeders as such, primarily because the question was asked earlier, price of uranium is too low, we don't really need to go into breeding, which is generating more material than you're using. I think they do have the technology, okay, the ability to operate on the fast end of the spectrum from a neutronic standpoint, has a definite application in our ability to better utilize spent fuel, essentially as burners as opposed to breeders.
Last question.
My name is John Melinda. I'm a renewable energy developer, also an alum of the nuclear program here at CMU, and also a Westinghouse alum as well. And Aris, you already answered half of my question when you said that the price of natural gas dropping delayed the development of nuclear power. I was going to ask about that, and I was going to ask, to what extent does the U.S. National policy on carbon emissions affect your predictions of growth for the nuclear industry?
What national policy?
That's my point. From the point of view of an energy developer, a renewable energy developer, those two things.
I think Kyoto Treaty.
Those two factors are the major factors affecting renewable energy development. And I wondered to what extent nuclear was immune from that, and to what extent they're also factors.
No, I don't think anything is immune from that. And I think when it comes to major infrastructure, and I'm an extreme when it comes to economics on the extreme right of that curve, but when it comes to infrastructure development, there is a role, and has to be a role, for some centralized planning. And right now, that's not well structured. It's probably the most polite way to put it.
Please join me in thanking our panelists. Thank you. We are now going to move right outside this auditorium, and there's a reception there right across from this auditorium in Tungau Labs. So please join us. Thank you.